Hello and welcome to our practical investigation on the factors affecting resistance. In our previous lesson, we've explored the fundamental concepts of electricity. You've learned about current, which is the flow of charged particles such as electrons, voltage, which is the potential difference that drives the current and causes electrons to move through a circuit, and resistance, which opposes the flow of current through the circuit. We've also discussed Ohm's law, which states that current is directly proportional to voltage and inversely proportional to resistance. We can express Ohm's law as an equation by using the equation for potential difference, which shows that potential difference equals current multiplied by resistance, or V equals I multiplied by R. We can rearrange this equation so that resistance is the subject. When resistance is the subject, we get the equation. Resistance equals potential difference divided by current, or R equals V over I. To understand the rearrangement of this equation, recall this triangle. This can be helpful for learning this equation for your exam. Today, we're going to expand our knowledge by investigating the factors that affect resistance in a conductor. Before we get started, let's briefly outline the importance of this practical. Firstly, the knowledge you will gain from this experiment is foundational for designing circuits with the desired electrical properties, ensuring that devices function effectively and safely. For instance, in the design of household appliances, automotive electrical systems, and even complex computer circuits, precise control of resistance can optimize functionality and energy usage. Secondly, knowledge of resistance is also essential for safety and energy efficiency considerations in electrical installations. For example, using wires with inappropriate resistance can lead to overheating, which poses a fire risk. Furthermore, high resistance in electrical circuits can lead to energy losses in the form of heat, reducing the overall efficiency of electrical systems. By understanding how different factors affect resistance, you can contribute to designing safer and more energy-efficient electrical systems, which is vital for both residential and industrial applications. On to the practical. Let's start by gathering our materials. Sam, what do we need?
So for this practical, we need a power supply, an ammeter, a voltmeter, wires of differing lengths, crocodile clips, a ruler, and finally, a lab book to record our results.
Once we have gathered our materials, we begin by setting up our circuit. We will connect our power supply to an ammeter and a voltmeter, as well as using crocodile clips to include a resistance wire. This is the circuit symbol format that we will keep a record of in our lab books. For our first circuit, we will be using a short wire. In this case, it is 10 centimeters. Make sure to carefully measure the length of the wire you use with a ruler. Now we turn on the circuit and record the potential difference and current as displayed on the voltmeter and the ammeter. Construct a table in your lab books to keep a record of these measurements. Once completed, we repeat this stage, but with a different length of wire. For instance, we could now place a resistance wire of 20 centimeter length in the circuit. Ensure to accurately record each repetition in your lab book. Also, be very careful not to touch the resistance wire whilst the circuit is connected, as it could be hot and therefore dangerous. Once you have completed numerous repetitions with different length wires, your table might look something like this. After about 10 different lengths, you can stop repeating the experiment and we can begin our analysis. We should have a table of data like this in our lab books. We can now use this along with Ohm's law to calculate the resistance. Recall that Ohm's law states that resistance is directly proportional to voltage and indirectly proportional to current, as summarized by the equation R equals V divided by I. Now, using this equation, we can input the values for potential difference and current, as we have them recorded in our table, to calculate the resistance for each length of wire. For example, for the wire that was 10 centimeters in length, we can input the values of 0.3 and 0.6 to get a total resistance of 0.5 ohms. Once we have calculated this for all the different lengths, we can fill in the final column of our table with these values. After calculating the resistance for different wire lengths, Plot these values on a graph with wire length on the x-axis and resistance on the y-axis. Each pair of values results in a point on the graph. When we draw a line of best fit, we can see a linear relationship where resistance increases as the length of the wire increases. This implies that the resistance of a wire is directly proportional to its length. This finding is intuitive. The resistance of a wire tells us how much it opposes the flow of electric current. When electrons move through a wire, they collide with the atoms in the wire, which causes resistance. If we increase the wire length, the electrons must travel through more material, which means they will collide with more atoms. This increases the overall resistance. So, a longer wire has more resistance than a shorter one. In today's practical, we investigated the factors affecting electrical resistance. Specifically, we measured the resistance of a wire by varying its length and observed the proportional relationship between wire length and resistance, which reinforced our understanding of Ohm's law and the dependence of resistance on the length of the conductor. Moving forward, remember the critical role that accurate data collection plays in understanding the behavior of electrical components. Mastery of these practical techniques will aid in future experiments, such as those investigating more complex circuits or additional properties of materials.